Okay, in this video, we're going to be looking at a problem where you're going to wind up needing to use that log rule. All right, so when you have one like question number 18 or question number 20, you can't rewrite 18 so that it's a problem that can be done by just using the power rule, because the denominator has two terms in it. So you can't just, get it to where it's three terms and you use the power rule to undo it. It's a rational function. Also, the top part looks more complicated, and when you do the derivative of it, you get like 4x plus 7, and it's hard to see where that would get you. That won't get you anywhere. That x minus 2 in the denominator would be a problem. So these are problems that wind up being ones where the log rule would be involved, but there's some work you would have to do ahead of time, and that would be to take the x minus 2 and divide it into the 2. This is the algebraic stuff that you would do before you tackled finding the integral of that. You would have to divide x minus 2 into 2x squared plus 7x minus 3. So I'm going to just use long division. X would go into 2x squared, 2x times. When I multiply back, I get 2x squared minus 4x. Okay. Now, let me stop here and say that this right here you can actually omit and not write down on your paper. You're not going to wind up having a question like this on the final, and I'm not giving any more tests in class. But you do wind up doing this a whole lot later, and so I am going to show you number 18 at least. So what you would do is you would do division. You take x minus 2 and divide it into 2x squared plus 7x minus 3. That does not factor. That numerator does not factor, so I'm actually going to use long division to rewrite it. So at this point, I'm going to come in and subtract that, what I just got from both terms. So I like to go ahead, when you're subtracting something, you can go through, change the signs so that you can think of it like an adding problem. So 2x squared minus 2x squared cancels out, and then right here, I get 11x. That's the reason when I teach how to do long division, I have you change the signs and then add, because that sometimes is where people mess up. All right, so now I'm going to wind up, having to bring down that minus 3. Now x goes into 11x 11 times. This is just like long division you used to do with numbers. Then I'm going to take the 11 and multiply back, and I'd get 11x minus 22. So the next step of the algorithm involves subtracting. So I'm going to come in here now and subtract. So that means that's like having a negative 1 that I'm going to distribute throughout. So that would change this to negative 11x and make the negative 22 into positive 22. So I'm going to add straight down now, and a negative 3 and a positive 22 would give me a positive 19 at that point. Okay, so this original expression that I have right here is equal to this mixed number. That's like an improper fraction that I'm changing into a mixed number. Just like 7 divided by 2, I could have used division to change that into the mixed number 3, and let me write it correctly, into the mixed number 3 1/2. That's kind of the process that we're doing if you want to try to make a little sense of it. So this would wind up being 2x plus 11 plus 19 over the remainder. Over the remainder gets put over what you were dividing by, just like here, right? So what I just wrote is equivalent to the original rational expression. And the reason we might do that is because we can do the integration term by term now. And so we know this came from x squared. We know this came from 11x. Okay. And then here we have a situation where we have a denominator. So that's going to wind up being a denominator to the first power, the x minus 2 to the first power. So that's going to wind up being just plus 19 ln absolute value of x minus 2 plus c. So anytime you're being asked to integrate and you've got these rational expressions where the degree on top here is greater than or equal to the degree of the denominator, and it's not factorable, the numerator's not factorable, then you typically will wind up using either synthetic or long division to rewrite the original problem in an equivalent form so you can use the power rule when possible. And then you wind up a lot of times having this little piece, 19 over x minus 2, that type of thing. And that's where the natural log would come into play. And so that would turn out to be the answer to it. Okay. I'm going to say here, again, you can omit this, but it's worth taking a glance at, especially if you're going to wind up doing more with this next semester. All right, so I'll go ahead and do this one. If I were trying to rewrite this one, I've got to put in a placeholder because it's missing a squared term on top. All right, now we do division in pre-cal and all, but it may have been a while since you've done it. So x goes into x to the third, x squared times, you multiply back. Okay, then you need to subtract. So I like to come in and change my signs. So I get my sign of, this is where everyone makes their mistake. So I make sure that sign is correct. I'm going to bring down the next term and go again. So then it would be minus 5x. That would give me negative 5x squared minus 25x. And I'm going to subtract all of that. So that would be the same as adding 5x squared and adding 25x. So the negative 5x squared and the positive 5x squared cancel. Negative 6 plus 25 would be 19x. Bring down the negative 20. Divide one more time. And I would get 19. When I multiply back, I'd have 19x. And then 19 times 5. 19 times 5, is that 95? Let's see. 50 plus 45. That's 95. Okay. And then I've got to subtract. So I'm going to change the signs. And I wind up with a negative 115 as my remainder. So that original problem can be rewritten so that I can use maybe some power rule on parts of this. Can be rewritten as x to the second minus 5x plus 19 plus, or you can do plus or you can do minus. I'm gonna do minus here. You can have plus with a negative 115 on top, but I'm going to do minus 115 over the x plus 5 I was dividing by. All right, so then I can do term by term integration. So this would become 1/3 x to the third. This one right here would be minus 5 halves x to the second. So I'd have x to the second divided by 2, but I already had that minus 5. Here I'd have a 19x. Here, I'm going to move this down a little bit so I have a little more room to write. Okay, come on. There we go. So I'm going to be doing it a little further down so there's more room to write. So this would be x to the third, but I've got to divide by 3 or multiply by 1/3. On this one, I would have an x to the second, but I already had the minus 5, and I would need to multiply by 1/2 as well. 19 would become 19x. And then here is the situation, just like on this one, where that x plus 5 to the first power in the denominator. So that's the one that's going to turn out to be a natural log. So it's minus 115 natural log, absolute value of x plus 5. Then throw the plus c in there, and you have it. Okay. All right, so I did a video on 5/8. If you watch that one first, then you've already heard me mention that the arc tangent, arc secant, and arc sine kind of come up. You wind up needing them because sometimes when you're trying to integrate a rational expression, you use division to do what I just did right here, and you'll get a term. It won't look like this because this doesn't need inverse trig functions, but you do sometimes get a term like this, and you wind up needing to use arctangent or one of the others in order to integrate. Okay. All right. Now, I'm going to go ahead and look at how you can use the log rule to help you integrate some trig functions. All right, so here's what's going on here. All right, you only know how to deal with integrating trig-related things that are related to the answer you used to get when you did derivatives back in chapter 3. Okay? So for instance, back in chapter 3, you knew that if you had a secant function, that the derivative of that would be secant x tangent x. You know that. So if you were trying to integrate something that was like secant x tangent x dx, okay, you could do it because that perfectly matches one of the derivative rules back from chapter 3. And you know that would wind up being secant x, and then you'd put the plus c on it. So far, there are some trig things that you've been asked to integrate. Things like sine and cosine, secant squared. You know, you could do anything that wound up matching what you got back in chapter 3 after you did the derivative. Okay. All right. What we're going to be able to do now is integrate something like tangent. And see, tangent is not the answer to any of the derivative rules back from chapter 3. Okay, so you will need to know these. I will definitely expect you to be able to do these because you can just figure them out. I'll show you what I'm talking about. So for instance, with tangent, see, tangent is defined to be sine over cosine. Right? And so I can think of that as 1 over cosine u times sine u du. So what I'm going to do is I'm going to think about letting this right here be, that's I can't use u because they already were using u, so let me use a v. Let that be, the denominator be some variable. Then if I did the derivative of that, I would get negative sine u du. Okay. And you see I have sine u du right here. So in other words, the numerator up here, the sine u, is going to come from doing the derivative of the denominator. All right. So I'm going to be able to do this usual thing that I did before, which is to divide by the -1 to get the sine u du by itself, and then make a replacement there. And what I'm really trying to integrate then is 1 over v times a negative dv. And so I'm trying to integrate something that is a log related deal. And so the answer would be negative natural log of v, which was cosine u, plus c. So you really could just use the log rule. You don't have to memorize these. You can just use the log rule to work these problems out. That's kind of what's going on. Okay? But if you wanted to, you could remember or figure out one of them, and then you would know what the other one is going to turn out to be. So it would be good to maybe know this one or be able to figure out that one, and to maybe know this or be able to figure it out, and then just notice the connection. So see how these are related. So tangent was the natural log of cosine, but it had a negative out in front. Cotangent, it's the natural log of sine, and it doesn't have the negative. Okay. And then the integral of secant, that's not the answer to any of the normal derivative rules for trig functions. Okay, but secant we know is 1 over cosine. So there's going to be a way you could figure out what the derivative would be, and I'm going to show you that right here. I'm going to give myself a little more room though. Okay, but then once I know that one or have figured that one out, I can see the connection between that rule and the one for cosecant. Okay, so here's what we could do to figure this one out. We could be thinking about, oh, well, this is really just 1 over cosine of u du. Okay. All right. So, and we could think, well, we're just going to try to do that. But when I try to do that 1 over cosine u du, the problem is I don't have the derivative of that cosine over there to do. So I was trying to do it kind of like I did that tangent problem, and I couldn't get it to work. All right. So what I'm going to wind up doing on this one is coming in here and trying to somehow get it to where this secant u tangent u thing, that shows up somewhere in the problem. Okay. So it's going to seem a little strange. It seems like that would work, but the reason it doesn't is I don't have the derivative of cosine sitting right here. Okay. So that's why that doesn't work. So what we do is this little kind of trick. I'm going to take this and I'm going to multiply by the secant x, secant u plus tangent u on the top and on the bottom. Okay. Well, right now I'm just trying to show why these rules turn out the way they do. All right, so when I do that, that numerator becomes secant squared u plus secant u tangent u all over secant u plus tangent u. Okay. All right, you see that? All right, so there what I could do is I could separate that if I wanted to, so that I have the secant squared u over secant u plus tangent u, and then the secant u tangent u over secant u plus tangent u. I could kind of separate it like that if I wanted to, but probably the easiest thing to do is to say, okay, well, let me let u equal the secant u plus tangent u. Okay, then I can do the derivative of this. The derivative of secant is secant u tangent u. The derivative of tangent is secant squared u. Okay. Oh, shoot. Can't use a u. I hate that. Let me change that to v, sorry. Okay, so v was secant u plus tangent u. So dv would be secant u tangent u plus secant squared u du. Okay. Now, do you recognize that right here? Okay. I see that piece. Okay. I've got the du over there. So I'm gonna be able to use the natural log in just a minute. So this problem is really 1 over secant u tangent u, secant u plus tangent u, times all of that du. So right now, this is not something you have to do. This is just showing why the rule turned out the way it did. Then you just have to be able to use that rule. Okay. So right here I have 1 over u, and right here 1 over v, and right here I have dv. So I'm just trying to integrate that. So it's going to turn out to be after I integrate, it's going to turn out to be the natural log of the absolute value of v plus c, and that's going to be the natural log of the absolute value of secant u plus tangent u plus c. All right. So we can derive these or figure out these formulas if we have to, but we do need to understand that little trick right there about multiplying top and bottom by secant u plus tangent u. And really, I don't think you would think to do that if you didn't already know this rule. Okay. So tangent is easy to figure out, but the secant and the cosecant one, I think those you just need to know. Okay. All right, I'm going to stop this video, and the next one is going to be much more straightforward because we're just going to be using those rules to do some more problems.